Okay, in this recording I will show an automated machine learning workflow for Excel data on PLS-DA method for supervised and unsupervised clustering. Usually we start with the data that looks like this. That's the entry number from the database, the ID, the formula, and the structure types. So here are 5 structure types. However, one structure type appears to be split into 2 groups, like the direct structure type and the anti-type here. Ignore the incorrect labeling here, we have it corrected somewhere else. So the key thing here is like our data should have the formula for labeling purpose, the structure type as a formula, which we later will convert to numbers, and a bunch of different interesting features over here. Okay, once we take our data and change the structure type from lettering to numbering over here, this is a machine readable format, since the first column will be ignored anyway as these are labels. The second column starts with a number in case if we are going to do supervised learning, so we know that the first structure is class number 1, the class number 2 is also the first structure but at the anti-type, and the third one is the different structure type, magnesium or silver arsenide or Hofhäusler, and so on and so forth. So we know what the labels are because we summarized them in something that looks like this. So we know which label corresponds to what structure. Anyway, so here we start in the terminal, and everything we need to do, we just need to type python main.py. If you just downloaded it from GitHub and starting for the first time, it might take a few minutes to initialize, but once you've done it first time, then you see how quick it is. So we just select the data that we just formatted, and since it is all user prompted, you don't need to do much here. You just need to follow the options and answer the questions here. So in case if we want to do classification here for the supervised learning, we just need to specify which column is our class. And as we formatted it in Excel, what we have here is simply the first column, which is automatically assigned as a label, and then it starts listing here all the columns in your Excel sheet from the second column, which is number 1 here in this example. So here we have our data. Again, as it mentioned, the first one is ignored as a label, and now it lists all of these columns here. Since the first one for classification problem is our class 1 through 6, we will indicate that column number 1, in this case structure, is our class. So we just need to say that it is column number 1 class. In this case, we don't need to ignore anything because it's usually reserved for some kind of comments or additional labels. So in this case, everything else are numbers, so we don't need to worry too much about it. And we can have a few options here. So normalization is usually the one we use. You can play with a little bit with auto-scaling or no pre-processing, depending on what your results are. In this case, I'll just use the second option. So here is like a quick result. It lists like what it reads and exactly what is going on here. And it lists your data, so you can just double check if it agrees with the number of rows and columns that you provided and so on. So we wanted to start with the supervised learning. That's why our next option is 2. We will just look at PLS-DA option only. That's why I'm just selecting one method. In case if you want a few methods, you can use like space separation in order to list them sequentially. But for our demo, we'll just use option number 1 here. So that's the number of components that we are going to consider. You can again just use a few different options like 3, 4, 10 or whatever you want, just to check if your results are different. I'll just stick to the default options, and you can see how quick it is. So accuracy doesn't seem to be very high, but keep in mind that PLS-DA is a very cheap method and it's very fast. So it also has the maximum explainability in it. That's why it is kind of expected that the accuracy won't be so high. But to be honest, this is quite a good result for PLS-DA classification without any additional modification of your data. So you have the detailed statistics outputted here. It also will be in another text file in case if you want to cite it and just learn more about like what precision recall is or any other things that you think is important to report. And it also tells you what the plot was generated and where it is saved. And if you're happy with that, you just say yes, because the option no returns you back to the other previous options where you can just specify the number of components and other parameters if applicable. So for this case, we're happy with the result. We just say yes. And the results are written to the, I believe, to the figures. So here's your classification plot. That's the one that is used typically for the report. You can see that these are classes 1 through 6 over here, keeping in mind the class 1 and class 2 are technically the same structure type reported, which with one of them being an antitype. So you can see here the separation is very wild, so it is very far from each other, which is kind of a good suggestion to start your data with type and antitype, assign it as two different classes. So everything else actually has quite a nice separation. Over here I don't see many problems. That's why 67% accuracy works quite well for this data. And additionally, the visual separation is important. So this plot is something that you can use for your report in case if you want, and also other information provided here. So this is for the classifier and the confusion matrix. So you can ideally want to see just a pure diagonal here in case if you see here 2 and 3, which has some misclassification here. You might want to take a closer look at your data and specifically why these structure types are misclassified. The members of these structure types are misclassified. Maybe they're structurally very similar to each other. Anyway, besides this helpful information, we're also getting some model statistics outputted here in a text file. And this is more or less the same that you've seen in the terminal window with some more additional information. Over here, this is some classification and misclassification here. Specifically here is only lists the compounds out of 300, only a few of them that were misclassified. So it just simply tells you what exactly was misclassification in terms of the class labeling here. And besides that, we have quite an important information about the components and the loading of each component. We already sorted here the components and their contributions so that the ones that contribute the most are listed at the top. As we can see, we can clearly separate the structure types based on a simple atom label distances. So for example, and specifically the homoatomic distances here for rare earth, transition metal, and metalloid distances. Over here they play the most significant role here. Actually, you can sort this component based on the numbers, because the higher the magnitude this number is, the more contribution it is. Oh yeah, probably made a mistake saying that it's already sorted. No, you probably need to sort it first based on this component, and then it will appear to you which properties are more important here. So we will do sorting based on the component 1, largest to smallest, which will reveal to you what was the most important factors there. So feel free to interpret all these information according to the chemistry that you observe in your system. Anyway, so these are the components that contribute to the plots that we've seen on a figure over here. So the component LB1 is the first component, and the factors you just seen them in the table. And classification results lists the full output. So for 66 or 67% accuracy, we would expect like 2/3 or even more than 2/3 actually classified correctly. Like for example, structure type 5, structure type 5, structure type 6, structure type 6. When there is a misclassification, we have the actual and predicted different numbers, and that's basically it. So this is a very simple way to use it without any programming knowledge. And what else we can do here? We can just try, since this is already quite a very good result for supervised learning, try to have like unsupervised one. We can start with main.py again. This time we select our data, and but we are going to ignore the class labeling, since we want to do unsupervised learning, and instead of it, we are just going to ignore the column number 1, which again is the structure type number 1 through 6. So this is the one that we are going to ignore, and we'll try to separate the crystal structures types without any information provided to it. This is what we call unsupervised learning, where we do not provide information about the structure types or even about the number of clusters that are present. So we will stick to the same normalization option. We want to do unsupervised learning, the option 1 here. And here is a very quick PCA plot. So since I already looked at a very similar plot from the previous study, so what I know that our one of the structure type number 1, it's probably like this block of points, and the structure type what we call number 2, or the antitype from the first one, is actually with somewhere within this cluster of points. So I know that they are already separated, but here we're trying to find out if we can automatically identify what kind of clusters and how many are present here. So clearly here probably will be identification of a 5 different structure, 5 different clusters as the first one, the second one, the third, the fourth, and the fifth, but it will depend on which method you select, because this is the plot of PCA, the principal component, based on this descriptors, but without any prior knowledge about how many structure types are present or what specific points, what do specific points belong to here. Okay, so just follow what the terminal tells you. So we need to close the plot to proceed. And after that, we have an option to select different methods. So feel free to experiment and try a few different methods here. It might give you different results, but I just want to show probably just only one, the k-means one. And you can either input the number of clusters, the ones that you expect. That's an interesting case. Here we have technically 5 structure types, but with antitype, it's technically 6. So you can input 5 or 6 here, and we'll try to find the appropriate clusters. Or you can use the elbow method, the ones that uses some statistics in order to determine what is the suitable number of clusters. So let's try to do this one. So this is what you're getting here, and it probably will make a cutoff somewhere at 1, 2, 3, 4, 5 structure types, I believe, because after the 5, the next 6 structure type, or the 6 clusters, sorry, it probably won't be very well separated. So it just looks at the curve, statistical curve here. So here we go, 5 types as it figured out, and it also said that probably these things belong to one structure type. Probably not what we quite expected, but again, if we just play a little bit with the parameters, we might get the separation that we are looking for. And specifically for structure type number 1, somewhere a cluster over here will be separate from some of the points from the other cluster. Anyway, if you're, you can look at different projections by just closing windows here, and different orientation, principal component 1, principal component 3, then 2 and 3 here, because in different orientations you might have a little bit better separation. But I'm not quite happy with the result, so I will just do it once again. And let's say you just want to specify that we have the number of clusters, 6, instead of the 5 that we automatically identified. So let's do that. And here is way better. Because most likely these yellow points over here, these are the anti-type for the large blob of the direct type points over here, cluster 1 and cluster 2, but we'll need to take a closer look at the results. So here is like an unsupervised learning to determine the clusters and where they are. So in case if you're happy with that, and especially different orientation, so different orientations probably won't give us a better segregation between the blue and yellow, but we don't know. By the way, this cluster numbering and its colors, they do not represent any specific order. This is just our 6 different clusters. So if we are happy with that, we can just simply look at the clustering results and confirm, is this something that we wanted to have or not. So for example, you can just cross-check your data and just double check if something that belongs to your direct type structure is well separated from, let's say, the anti-type. So here I will probably just look at my Excel sheet from the original data, and this is structure type number 1, and it looks like the sample number 55. It just changes to a different structure type. Look at it. So here it is. So this is quite a good result. Again, don't look at the actual numbers 1 and 5, 1 and 2, because it didn't know what is the numbering you're actually looking for. So this is quite a significant result here, since we have like an ideal unsupervised learning separation of the anti-type from the direct type. Again, looking at what we're considering here, copper, hafnium 5, tin 3. These are compounds 1 through 54 row, and starting from row 55, we actually have the anti-copper hafnium 5 tin 3 type. And let's see if the end of this cluster actually matches to what we are getting in unsupervised learning. So it should be somewhere around like 97, and here we go, ideal. So in other words, with the machine learning, which is more important with unsupervised machine learning, we can actually work with the structure types reported as the same structure type, copper, hafnium 5, antimony 3, and identify, without any knowledge that we provide to the model, any additional chemistry provided besides the features, we can identify that within that structure type we can have occurrences of the anti-type cases. And the unsupervised modeling that can capture this information is actually quite helpful. We can double check the rest of the classification later, but I will stop my recording right here.